All right, y'all. Today we are going to talk about the relationship between differentiability and continuity. So please make sure you get the title of your notes. And then you do not need to write this down right here, but you need to make sure you understand what it means. So go ahead and just listen. Differentiability at a point. First of all, you should write down differentiability. If a function is differentiable means differentiable means you can take the derivative. You can take the derivative. All right, you should know that, so write that down. Sweet. Now let's talk about what differentiability at a point looks like. So a function y equals f of x is differentiable, or you can take the derivative at the point or at the x value, x equals c, if and only if, and then we have this crazy limit looking stuff where L is a finite value. Okay, so what is this crazy limit looking stuff saying? Well, this limit is a definition of the derivative, and that limit is saying from the left. So this is the derivative from the left, and then this is also the definition of the derivative, one of the limit definitions of the derivative, but that limit is saying from the right of c, and then this number in the middle, this is just a number that they're calling L. So what is this saying? A function is differentiable at a point if the derivative from the left equals the derivative from the right. That's it. Now, one thing you need to remember is the derivative is the slope of the tangent line. So the slope of the tangent from the left, on the left of C, equals the slope of the tangent on the right. On the right of C. And that's C is an x value. Okay, so it's kind of like continuity. The limit from the left has to equal the limit from the right, but differentiability is the slope has to be the same on the left and the right. All right, and then a function will not have a derivative, so you should write this down. There is no derivative at a point where you have a corner. Here's the times that you have no derivative. When you have a corner, which is the same as a sharp point on your graph, a cusp, and let me draw these actually. Corner looks like this, or like this. A cusp is kind of like a corner, but it's like curvy. Woo, that's a cusp. Could also go this way, right? A vertical tangent line, so a vertical tangent would look something like this. You could have your function like going a variety of ways. Or a discontinuity of any kind. So you could have like a removable discontinuity, for example. You can't take the derivative at the removable discontinuity. Okay, so you have no derivative if you have any of these things that I just drew. No derivative exists at points where those happen. All right, and why? Because. Why is there no derivative? Because the slope of the tangent line from the left does not equal the slope of the tangent line from the right. All right, so let's look at some examples of where that occurs, where there's like no derivative. Okay, examples of functions that are not differentiable at specific x values. And it would be helpful for you to get a sketch of these in your notebook. You don't have to draw them exactly, but obviously this is like an absolute value graph. It's a v, so draw a v. All right, and this function is not, and we're going to abbreviate differentiable, diffable. So this function is not differentiable at what x value? At x equals what? This function is not differentiable at x equals 1 because we have a point. There's a sharp point at x equals 1, but we're not allowed to tell the AP Calc graders, oh, it's not differentiable at x equals 1 because there's a sharp point. We're not allowed to say that. We need to say because the tangent on the left of 1 does not equal the tangent on the right. And really the best way to say that, so like this is kind of like layman's terms, but the way that we're going to say it for the AP exam, this is how we say y. Because the limit as x approaches 1 from the left of the derivative, that's a tangent. That's the slope of a tangent line. It is not equal to the limit as x approaches 1 from the right of the derivative. These slopes do not equal on the left hand and the right side. See, look, let me show you. The slope from the left is like -1, right? M equals -1. But the slope from the right, M equals +1. Those aren't equal, so we cannot take the derivative at that point where x equals 1. Sweet. Let's do this graph. So, what point is this function not differentiable at? X equals 0. Why is it not differentiable at x equals 0? Because we have a vertical tangent. Oh shoot, y'all, on vertical tangent line, I drew a vertical asymptote. Vertical tangent line would look like this. Right here, the tangent is vertical. I just realized that. Sorry. Okay, so this is not differentiable at x equals 0 because we have a vertical tangent line at x equals 0. And it's for the same reason. So we're going to say because limit as x approaches 0 from the left of the derivative. So that's the slope of the tangent line on the left. Let's go ahead and draw that. Slope of the tangent line on the left would be like this slope, right? It's a positive slope. It's pretty steep. That does not equal the slope of the tangent line of the derivative. The slope of the tangent line, sorry, the derivative on the right-hand side, that slope would look something like this. They're not equal. You don't have slopes from the left and right equaling each other. All right. And the last one, derivatives don't exist at any type of discontinuity. A vertical tangent is a type of discontinuity. This is a discontinuity. This is not continuous at x equals -2. So what we're going to say is this function is not differentiable at x equals -2. And then we have our same reasoning because the limit as x approaches 2 from the left of the derivative does not equal the limit as x approaches 2 from the right of the derivative. And let me show you with the slopes of the tangent lines. Tangent line from the left. Well, actually, this one, it's kind of hard to describe why. Really, you just can't take the derivative. You can't find a slope of, there's no tangent at x equals 2. There's no curve to like draw a tangent on, right? So, we're just going to say, you could say, really the easiest way to answer this one is because f of x is not continuous at x equals 2. So I would say like forget this explanation. And that kind of leads me into our next fact, which is differentiability implies continuity. Okay, so if f is differentiable at x equals c, then f is continuous at x equals c. That's important, so you should write that down. If you can take the derivative at a point, then that means your function is continuous at that point. And so that means differentiability implies continuity. But you need to know something. It is possible for a function to be continuous at x equals c and not differentiable. It is possible for a function to be continuous at x equals c but not differentiable at x equals c. So what does this mean? Let's go ahead and stamp it a little bit. So just because a function is continuous, it's not differentiable. It's not necessarily differentiable. Just because it's continuous, that doesn't mean it has to be differentiable. Okay, let's go ahead and describe some x values on this graph where this function is differentiable. So we want to know, where is this differentiable? All right, let's look at all of our curve. So it looks like we're good here. We're differentiable here, 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 here. The points in question are right here, right? We're not differentiable at sharp points. And I can go ahead and tell you that those points happen at negative square root of 5 and positive square root of 5. So the way that we would answer this question is g of x is differentiable everywhere. It's differentiable for every x value everywhere except x equals negative square root of 5 and x equals square root of 5. You could also write intervals, right? So we could say from negative infinity to negative square root of 5, we are differentiable, and from negative square root of 5 to positive square root of 5, and from square root of 5 to infinity. And we have parentheses here, parentheses, to imply that we are not differentiable at those points. If we had brackets, then it would say that we are differentiable at those points. Okay, let's move on to a different type of problem. And you need to make sure you have this whole example down. So write down your function f of x. We are going to find the derivative function f prime of x. And then we're trying to answer the question, is f continuous at x equals 0? All right, and let's go ahead and start. So the way that we're going to prove continuity is we're going to do the same, or differentiability is we're going to do the same steps as continuity. So let's go ahead and prove continuity first. Is f continuous? And if you remember those steps, we should remember those steps. The first step for continuity, sorry y'all, I'm trying to zoom out. Okay, first step for continuity was, does f of the x value that's in question exist? X equals 0. So does f of 0 exist? F of 0 equals, we could plug into this function, so we get negative 2 times 0 equals 0. Yes, f of 0 exists. Second step for continuity, does the limit from the left equal the limit from the right? So let's find the limit from the left. That is the limit as x approaches 0 of the left function. The left function was negative 2x, which we already found, that's 0. The limit from the right, so x approaches 0 from the right, equals the limit as x approaches 0 of the right piece, so that would be 2x, which equals 2 times 0, also 0. So these equal each other, right? Yes, we're good. And then the third step for continuity is, does f of 0 equal the limit as x approaches 0 of f of x? Yes, because 0 equals 0. We got 0 for all of our pieces, right? Okay, cool. So, yes, this function is continuous. We would say yes. The answer to this question is yes. This function is continuous at x equals 0. Now we're going to answer the question, is f differentiable at x equals 0? Okay, so the way that you do differentiability, the way that you prove differentiability, you're going to do step 2. Do step 2 of like the continuity test, but do it for the derivative. So if you want, you can write that down. Step number 2, but for f prime of x. So the first thing we need to do is find f prime of x. So go back up to the top. We're going to write f prime of x. This is a piecewise function. F of x is piecewise, so f prime is also going to be piecewise. So let's go ahead and do our curly brackets. And then we're just going to take the derivative of the top piece and the derivative of the bottom piece. So the derivative of negative 2x is negative 2. And then I don't have time to explain why, but we drop the equal to sign, so we're just going to say negative 2 for x is less than 0. You drop the equal to sign when you take the derivative. And the derivative of this bottom piece, the bottom piece here is 2x, or sorry, 2. Derivative of 2x is 2 for x is greater than 0. Okay, so now that we have f prime, we can do step number 2, but for f prime to check if the function is differentiable. All right, so let's go ahead and do that. Step number 2 is, I'm going to just go ahead and write 2, the limit as x approaches 0 from the left of f prime of x. So what is the limit from the left? Let's go ahead and look, make sure we know what our left function is. This is our left function. So equals -2. That would be the limit of -2. That's the left function. Equals -2. Now let's do the limit as x approaches 0 from the right of f prime of x, the derivative function. And that's the limit as x approaches 0 of the right piece. Right piece was 2. So of 2. And the limit of a constant is just that constant, so 2. Sweet. Do these limits match? Does -2 equal 2? No. So we are going to write the limit as x approaches 0 of f prime of x does not exist. Because because the limit as x approaches 0 from the left of f prime of x does not equal the limit as x approaches 2 from the right of f prime of x. -2 does not equal -2. So, is this function differentiable? That's what we're trying to answer here. Is this function differentiable at x equals 0? No. No, it is not. The limits have to be equal for the derivative. The limits of the derivative have to be equal. So we would say no. F of x is differentiable everywhere except x equals 0. Everywhere except x equals 0. Okay. We're going to do a couple more like this, and I'm going to go quickly through them because we're basically going to follow the same process. So let's get the next one down. Example number 2. We have g of x equals 8x minus 3 if x is less than or equal to 1, 4x squared plus, that's a 5, if x is greater than 1. All right, is g continuous? So we're going to very quickly go through these steps. 1, g, make sure you're using the correct function. So g of 1 equals, well, g of 1 is 8 times 1 minus 3, which equals 5. So cool, g of 1 exists. Let's find step 2, the limit as x approaches 1 from the left of g of x equals the limit as x approaches 1 of the left piece, which is 8x minus 3, which equals, we just did that one, 5. Plug in 1. All right, and then the limit as x approaches 1 from the right of g of x equals the limit as x approaches 1 of the right-hand piece, which is 4x squared plus 5. And if we plug in 1, we get 4 times 1 plus 5. That's 9. Uh-oh, check it out. These limits don't exist. Or the limit, so let's conclude, those don't equal each other. So the limit as x approaches 1 of g of x does not exist. So g of x is not continuous. Okay, time out. Didn't we just learn something about continuity and differentiability? Can a function be differentiable if the function is not continuous? No. So, is g differentiable? No. So we say g of x is not continuous. So, g of x is not differentiable. We need to say at the specific x value that we are looking at. So we are looking at x equals 1. So g of x is not continuous at x equals 1, and it is not differentiable at x equals 1. Cool. Let's move on. We have 2 more. All right. H of x equals x squared minus 4x plus 8 if x is less than or equal to 3. And then 2x minus 1 if x is greater than 3. Is h of x continuous at x equals 3? All right, let's go through our steps. Step 1. We have, let's see. We have h of 3. Yeah, 3 equals 3 squared minus 4 times 3 plus 8, which equals 5. 2. We need to find the limit as x approaches 3 from the left of h of x, which equals the left piece. I'm just going to plug 3 into the left piece right now. That is what we just found, 5. Limit as x approaches 3 from the right of h of x. I'm going to plug into the right piece right now. That's 2 times 3, which is 6, minus 1. I'm plugging into this piece, which is also 5. So these do match. That's good. And they also match with h of 3. So we're going to say h of x is continuous. It is continuous at x equals 3. Sweet. Let's move to the next question. Is h differentiable at x equals 3? Well, the first step is to find the derivative of h of x. So let's go ahead and find h prime of x. And it's going to be 2 pieces. We're going to take the derivative of the top piece using the power rule. So we have 2x minus 4 if x is less than 3. And then we'll take the derivative of the bottom piece. Derivative of 2x minus 1, that's just 2 if x is greater than 3. And now we need to check, is this function differentiable? So we're going to do step 2, the limit step, but for the derivative. So limit as x approaches 3 from the left of h prime of x equals, and we're going to plug into the left piece. So the left piece was 2x minus 4 equals 2 times 6 minus 4 is 2. Now let's check the limit from the right. Limit as x approaches 3 from the right of h prime, the derivative, equals the limit as x approaches 2 of the right piece, which is 2. And the limit of a constant is just that constant, so 2. These also equal each other. 2 equals 2. So guess what? So our conclusion, we could say like the limit exists, right? We could say limit as x approaches 3 from the left of h prime of x equals the limit as x approaches 3 from the right of h prime of x, which equals 2. So h of x is differentiable at x equals 3. Yay! All right, now for the hard part. The hard part is one of kind of like our old examples with continuity. So this is really important. Write down this whole example. Make sure you get this example down. We only have one more example left. F of x equals the piecewise function 3x squared plus 4x if x is less than or equal to 1. 2x cubed plus, now we have b and c, bx plus c if x is greater than 1. All right, and we're trying to find b and c so that f is continuous at x equals 1. Okay, we're trying to prove continuity, and now we have two missing pieces, b and c. We used to just have one. So here's what you're going to do. You're first going to prove continuity. So let's first do continuity using all of our steps. So step 1, we have f of 1 equals, we could plug into the top function, so we get 3, 1 squared plus 4 times 1 equals 3 plus 4 is 7. All right, f of 1 is 7. Step 2 for continuity. The limit as x approaches 1 from the left of f of x equals, I'm going to plug into the left piece. Actually, I should probably show this. So we have the limit as x approaches 1 of the left piece, which is 3x squared plus 4x, which equals, we already found that, 7. Now we need to find the limit as x approaches 1 from the right piece of f of x. which equals the limit as x approaches 1 of the right piece is 2x cubed plus bx plus c. All right, we're plugging 1 into x, right? So equals 2 plus b plus c, right? We plugged 1 into the x's. All right, 2 plus b plus c. And for continuity to be true, for the continuity to actually be a thing, we need these three things to equal each other, right? So we're going to set them equal. We're going to say, okay, 7 has to equal 2 plus b plus c. But here's the problem. We have two missing variables now. So what do? We use the steps to prove differentiability now. So let's go ahead and do that. Step 2, we're going to do differentiability, and you'll see how this saves us. Okay, first step for proving differentiability, we need to find f prime of x. So we know it's going to be a piecewise function. Let's go ahead and find it. I'm going to just look and do it down here. So f prime of x, the top piece is 3x squared plus 4x. The derivative of that by the power rule is 6x plus 4. And that's for x is less than 1. The bottom piece, we have 6x squared. And then b is a constant, y'all. So if it's a constant on x, the derivative is just that constant. So plus b, the constant. And then the derivative of this constant is 0, right? So that's our derivative, 6x squared plus b for x is greater than 1. Sweet. And now we're going to go through the steps of continuity for our derivative function to prove differentiability. So actually, we're just doing, remember, we just do the second step of continuity. So we're going to do the limit as x approaches 1 from the left of f prime, which equals 6 times 1 plus 4, which equals 10. Sweet. Now we're going to do the limit as x approaches 1 from the right of f prime, the derivative function of x, equals, we're plugging in 1 to x, so we have 6 times 1 squared plus b. For this function to be differentiable, we need these two to equal each other. So let's set them equal. So we have 6. This is just 6 plus b. True. So let me go ahead and fix that. Oops. 6 times 1 squared. Okay. We want 6 plus b to equal 10. So let's set those equal. Plus b equals 10. And now we can actually find the value of b. So subtract 6 on both sides. What does b equal? B equals 4. Yay, we have b. Now guess where we could put that? We can take the value of b and plug it in up here. So b equals 4. Plug that in right here, and then we can find c. So let's put it all together. Let's do that over here. We have 7 equals 2 plus 4 plus c. Subtract 2 plus 4, subtract 6. 1 equals c. All right, we found the value of b and c that make this function continuous and differentiable. All right, and that's everything for today, y'all. Good work.